Okay, welcome back to another physical sciences lecture. So we have, in the previous lecture, we looked at just an introductory to motion graphs. And this one we're looking at displacement versus time. So we went over this information. So just to recap, if we're looking at displacement versus time, we can read directly from the graph displacement and time. And we can also calculate the velocity from the gradient. Okay, so in these examples, we will be looking at the gradient, the velocity, and comment on the displacement, velocity, and acceleration in order to describe the motion present by each graph. Okay, so if we look at this, graph here, so this first graph, we have a constant displacement. S is equal to 10. So remember that velocity is equal to displacement over time, and it's the change in displacement over change in time, or change in displacement over time. And if there's no change in the displacement, then the velocity is equal to 0. Okay, so velocity is equal to 0, and that's because the gradient is also equal to 0. So we can say the change in displacement is change in time. Gradient is equal to 0. That means velocity is equal to 0. So all that we can really say here is that the displacement of an object is 10 meters north. 10 meters north of a reference point. A reference point. And we can say the object remains stationary for 8 seconds. So that's 8 there, 8 seconds. So we can say the object is stationary for 8 seconds. Or at rest. I might say at rest rather than stationary. The object is at rest for 8 seconds. Okay, and that implies that acceleration is also equal to 0. All right, let's have a look at this second graph here. Okay, so because we have a straight line, it means that the displacement is changing constantly, which means that the velocity is also constant. And then it means that the acceleration is equal to 0. So remember that acceleration is equal to the change in velocity over change in time. So it means that, so for this one here, we just need to work out v, which is equal to the rise over the run. And we can just go here. So it goes up 20. So rise is 20 divided by the run here, which is 10. So remember, this is the rise. And this is the run. Okay, so rise over run equals 20. So that's equal to 2 meters per second. And remember, with a velocity, it's a vector. So we need a direction too. So this is 2 meters per second north. And acceleration equals change in velocity over change in time, which is equal to 0. Okay, that's because we've got a constant velocity. So we can say that an object travels north at 2 meters per second for 10 seconds. So an object travels north at 2 meters per second for 10 seconds, so that its final displacement is 20 meters north. Okay, good. Okay, so notice in the last example, we had a positive gradient, which meant we had a positive velocity, so it was traveling north. In this example here, we have a negative gradient, so we're going to have a negative velocity, and in this case, a negative velocity is equivalent to a velocity in the southerly direction. So we're doing this graph here. We can start by calculating v, which is the rise over run. And my rise is going to be, I'm just going to do this point here, so that's our rise, which means that's our run up there. Okay, so the rise here, that's equal to -10. So it goes from 10 down to 0. So we've decreased by 10. And our run is a +5. So that means that we've got -2 meters per second, which is equal to 2 meters per second south. Okay, so this was a northerly, that's north direction, and this is a 2 meters per second south. Again, it's a constant straight line, so our acceleration is equal to 0. So in this case, we can say an object starts at 10 meters north. So that's our displacement. Displacement is 10 meters north up here of a reference point. And then we can say it travels 2 meters per second south for 10 seconds. 2 meters out, 2 meters per second, travels 2 meters per second south for 10 seconds, having with a final velocity, sorry, I keep saying final velocity, with a final displacement of 10 meters south. And you may, in some questions, be asked, what does this point at 5 seconds mean? And what that means is it passes the reference point or the starting point at that time. Okay, so at 5 seconds, we can say that at 5 seconds, the object passed the reference point. Okay, so a reference point is just maybe someone's observing. There might be someone measuring the. It might be like the start or finish line of a racetrack or something like that. So we can imagine that if it was a racing track, or there might be someone at this point here, and the starting line for them might have been 10 meters north, and then someone's timing from this reference point here, and then someone runs past starts at 10 meters north, then runs past them and goes past them at 5 seconds, and continues for another 5 seconds. So end up 10 meters south, something like that. Okay, so we'll do this final one in this video, and then we've got a more detailed problem to do in our next video. Okay, so in this one here, just notice that this time we don't have a straight line, which means that we have an accelerating point. Okay, we're not expected to actually. You can calculate the velocity at points. I don't have my ruler with me, unfortunately, but if you did like a straight line, that's not a very good one. We want a straight line that kind of just touches that. So if you're ever asked to calculate the velocity at a certain point on this graph, you'd have to draw a straight line at a tangent. We say this is a tangent, and then you can calculate the rise over run of this straight line. And then we could calculate an instantaneous velocity at any point along this curve. But we won't do that in this case. All we need to say really about this one is an object. We can still see what our points are. So that's it's about 9 meters, I would say. It's roughly 9 meters north after 6 seconds. So that's 6 seconds. So what we can say is an object accelerates away at M on N. So we can say it accelerates northwards from a starting point such that its final displacement is 9 meters after 6 seconds. Okay, that's all we really need to say about that one. Okay, now I think, yeah, so the next one's an example, and we'll leave that for our next video.